In this lecture, which is lecture 30, I'm going to continue with section 11.1. We will finish it today. So remember that we're talking about sequences, and I'm going to state a result that we can use, and afterwards do an example or two. Okay. Okay, so let's recall the notation for last time. So we have sequences, A sub n, and sometimes we indicate the indices, n goes from 1 to infinity, and then we wrote the limit of A sub n as n goes to infinity is L if it converges, otherwise it diverges. Okay, so I want to talk about some properties that a sequence may or may not exhibit. So a property I want to talk about is, this is a definition, a sequence A sub n is said to be increasing if the nth term of the sequence is always smaller than the next term, the nth plus first term of the sequence, for all n, and of course n is starting at 1, so for all n bigger than or equal to 1. Now, not every sequence is increasing, obviously, but I want to we have a companion definition. A sequence A sub n is said to be decreasing if A sub n, the nth term, is larger than, it should be a strict inequality here, so let me change that. Strict inequality in both cases. If the terms are getting smaller as you move along the sequence. Okay, so here's some examples. 1 over n. So this is the sequence 1 over 1, 1 over 2, 1 over 3, etc. This is obviously decreasing. The fractions are getting smaller. So another example would be the sequence n itself. That would be 1, 2, 3, 4. That would be increasing. Another example would be -1 to the n. That's the sequence -1 plus 1 -1 plus 1. That's neither increasing or decreasing. So that's no good. I want to add to the definition. We'll say that a sequence is monotone if it is either increasing or decreasing. So one or the other. It can't obviously be both. That doesn't happen. Okay, so that is the definition, the basic definition of sequences. Now, one problem you may be given is to show a certain sequence using algebra or some other technique to show that a certain sequence might be increasing or decreasing. So let's give an example. An example would be n over n squared plus 1. Now, to get an idea of what's going on with this, adding 1 to the denominator for large values of n is really negligible. So this is behaving like it would be n over n squared. It's sort of like n over n squared. The word like is in quotations. And that's 1 over n, and 1 over n is decreasing. So you would guess that this might be a decreasing sequence. So let's show this is actually, in fact, decreasing. So I want to show you why it's decreasing. So the nth term is a sub n is n over n squared plus 1, and we need to show that the nth term for all n is bigger than the term after it, which would be n plus 1 divided by n plus 1 squared plus 1, because that would be the nth plus first term of the sequence. So this is what we have to show. So we don't know this is true. We have to show it's true. So I'm going to put a question mark over the inequality. And we just have to use the rules for manipulating inequalities to see whether or not this is true. So what I'm going to do is I'm going to multiply both sides by the denominator on the left and the denominator on the right. That does not change the direction of inequality if the inequality holds. So this would be asking the question as to whether n times n plus 1 squared plus 1 is bigger than n plus 1 times n squared plus 1. So we're looking for, I'm going to make this question mark in a different color just so you know it's questionable, this question mark. Okay, so we have to do some algebraic manipulation. It's not hard, but we have to do it. So the left side becomes n times n squared plus 2n plus 1 plus 1. So that's in the parentheses times the n on the outside, and that's supposed to, we're asking whether or not that's the same thing as bigger than, sorry, the product here, and the product here would be n cubed. Oops, I don't want that. It would be n cubed plus n squared plus n plus 1. That's what you get when you multiply this out on the right. Okay, and now what I'm going to do is I'm going to go on the left side and distribute the n in. So that would be n cubed plus 2n squared. Okay, so n1 plus 1 is 2, so that gives you a 2n when the n is distributed in. And you want to know whether or not that's greater than n cubed, oops, plus n squared plus n plus 1. Okay, so now you can subtract n from both sides, n cubed from both sides. You can subtract n from both sides. And you can even subtract n squared from both sides. So you can subtract the first three terms here on the right from both sides. What do you get? So you're going to be left with n squared plus n, and you want to know whether that's bigger than 1. So that's the question mark. And the answer is, since n is varying from n is equal to 1, 2, 3, etc., every value of n has this property that it's bigger than 1, because n squared plus n is the same as n times n plus 1, and that's always bigger than 1. So this checks out. This works. So we've just reduced the inequality we had to show to another simpler inequality, and now you just backtrack to get back to the original inequality, which we've now established. So this shows that this is decreasing, which is what we wanted to show. Okay. All right, so now there's another method for showing that the sequence is decreasing, and it's sort of simpler. That was method 1 before. Now I'm going to give you method 2. So we want to show that n over n squared plus 1 is decreasing. So what I'm going to do is, let's look at the function x over x squared plus 1. I'm replacing n, which is an integer, by any real number x, and I want to look at this function. Let's call it f of x. So it's enough to show f of x is decreasing as a function for x at least 1. And this is actually, we can do this with calculus 1, in fact. So what we're going to do is we're going to take the first derivative and look at the sign of the first derivative. So f prime of x by the quotient rule is the bottom times the derivative of the top, which is 1, minus the top times the derivative of the bottom over the bottom squared. And what does this give us? This gives us x squared. This gives us, it looks like, a 1 minus x squared over x squared plus 1 squared. Now, if x is bigger than 1, x squared is going to be bigger than 1. The denominator is always positive. So this is always going to be less than 0 for x bigger than or equal to 1. So then that means that f prime of x is negative for x greater than or equal to 1. So that means that f prime of x, f of x, not f prime of x, is decreasing. Oops, this is ugly. For x greater than or equal to 1. That's all we have to show. So we're done. This method 2 was much easier in my opinion. Okay. Okay, so the next property I want to talk about is boundedness. So a sequence is a definition. A sub n is bounded above if what? If there is a number m, is a real number m, such that all the terms of the sequence are less than or equal to m. So for all indices n. So every term of the sequence is smaller than the number of n. Okay, so that's the bounded above definition. There's also similarly a bounded below. So a sub n is bounded below if there's a number, say lowercase m, such that m is always less than or equal to a sub n. Okay, so then here's the cruncher. Okay, so a sequence a sub n is just said to be bounded. So bounded if if it is both is important, bounded above and bounded below. So you need both conditions. So it makes sense to try to look at a couple of cases to get a feel for this property, okay, this definition. Okay, so for example, let's look at the sequence 1 over n. So that's 1, 1/2, a third, etc. Now these numbers aren't, every single number in the appearing in the sequence is never larger than 1. So 1 over n is always less than or equal to 1. But every number in the sequence is also not negative, so it's always greater than or equal to 0. This is for all n equal to 1, 2, 3, etc. So this sequence is bounded, both above and below. So it's bounded. Here's another example. -1 to the n. This sequence. So that would be -1 plus 1, -1 plus 1, -1 plus 1, etc. So it's bounded. So if this is a sub n, it's -1 to the n, that's certainly less than or equal to 1, and it's certainly greater than or equal to -1. So this sequence is bounded. Okay, but here's an example of something which isn't bounded above, n squared, right? That would be 1, 4, 9, 16, 25, I'm squaring the integers. This is not bounded above. It is bounded below by the number 1 even, right? Okay, so these are a couple of examples, and I want to state the main result. So I'd like to state something called the monotonic sequence theorem. It says this, it's very simple. Every sequence which is both bounded and monotonic both properties must hold converges. This is a key feature. So it has to be bounded and it has to be monotonic, and then it guarantees convergence. Now, there are sequences which are not bounded or not monotonic, which also converge, but this is telling me if I have a sequence which is both bounded and monotonic, that guarantees converges. Now, this might be called a qualitative result. It does not tell you what the sequence converges to. It just says it converges. It just claims that it converges. Okay, and that's an important point. So this is a qualitative result. All right. So I'd like to now turn to an example or a problem in the text. So let me pull up the text. Okay, so I'd like to draw your attention to problem number 89 in the text in section 11.1 in the exercises section. It says this: Fibonacci, who was an Italian mathematician, posed the following problem. Suppose that rabbits live forever and that every month each pair produces a new pair which becomes productive at age 2 months. So every pair of rabbits, the rabbits that start in month 1, if you wait 2 months, they will produce. Okay, they will reproduce. And the question is, if we start with one newborn pair, how many pairs of rabbits will we have in the nth month? And it shows the answer is f sub n, where f sub n is the Fibonacci sequence. And then there's a part B, which asks us to find the limit of the Fibonacci sequence. So that's what I'm going to consider solving here. Okay, so what I'd like to do is consider the situation. Let's look at the first few months, first of all. So let's see, this is problem number 89, part A. So in month 1, you start off with one pair of rabbits. So I'm going to indicate that by a hash mark. So this is one pair. So what happens in month 2? Well, your one pair cannot reproduce. So how many pairs do you have? You still have one pair. So then in month 3, what happens? In month 3, the pair that existed in month 1, it now reproduces. So now you have your original pair and then a new pair. So now you have 2 hash marks. Okay, so that's month 3. So now what happens in month 4? Well, actually, maybe it makes sense to give a different color to the pair that was reproduced. So let me put that in yellow. So now we have the newborn pair is in yellow, and the black one is my original pair. So now what happens in month 4? In month 4, my black pair can reproduce again. So then I get 2 pairs. Okay, so I want to do that in black. So, and then I have a rabbit, a new pair, which I'll write it in green, and then we have my yellow pair. Okay, so the yellow, there are two yellows on the board. That means in the 5th month, what happens? My black one will reproduce. So my black one exists. He's going to live forever, my black pair. And there's a new one. And then the green one cannot reproduce yet, but the yellow one is now allowed to reproduce because its 2 months have passed. So I'm going to get a yellow, and oops, that should not be green. That should be yellow. And then we get another color, which I might call blue. So let's count up what's happening here. So in month 1 we have 1, in month 2 we have 2, 1, 1, 2, 3, 5. So we have 1, 1, 2, 3, 5. It starts off looking like the Fibonacci sequence. Now what's going on in month n minus 2? Well, you have maybe a certain number of pairs available in month n minus 2. And then you have month n minus 1. And let's say the number in month n minus 1 is denoted fn sub n minus 1. So now what happens in month n? Well, the rabbits that in month n minus 2 that exist in month n minus 2, these here, are all able to reproduce. The ones in n minus 1, these are the new rabbit. I should probably call these, yeah, hold on. So what I should be saying is f sub n equals the number of pairs that exist in month n. So in month n minus 2, we have fn minus 2 pairs, and month n minus 1, say we have fn minus 1 pairs. How many do we have in month n? Well, every rabbit pair in the n minus 2 month is now allowed to reproduce, and none of the others can reproduce that come. So we get an extra copy of the n minus 2 rabbits occurring here. So we get fn minus 2 plus fn minus 1. Hey, that is exactly how the Fibonacci sequence is defined. So this shows you get the Fibonacci sequence. Okay, very good. So now, what we have is part B of the problem, which is, it tells us what to do. Let's set A sub n, but let's make it the quotient of the number of rabbits in the Fibonacci n plus first term divided by the Fibonacci nth term. And so let's see what you get. So A sub n is fn plus 1 over fn, but fn plus 1 is given by fn plus fn minus 1, and we're dividing that by fn, so that's going to be the same thing by breaking up the fraction fn over fn, which is 1, plus fn over fn minus 1 over fn. Now, fn minus 1 over fn is the reciprocal of a sub n minus 1. So this is 1 plus 1 over a sub n minus 1. So this essentially does part B, the first part of part B. Now, it says, assume the sequence a sub n converges. So let's assume a sub n converges to x, to some x. Okay, so what does that mean? Well, we can look at, so then what happens to this boxed off equation? Well, the left side, when we take the limit, so let's take the limit as n goes to infinity of a sub n, that's going to be the same as the limit as n goes to infinity of 1 over a sub n minus 1. But now the limit as n goes to infinity of a sub n is x. So that's x. And here the limit by the limit rules give you 1 plus 1 over the limit as n goes to infinity of a sub n minus 1. But that's the same as a sub n going to infinity. So it's 1 plus 1 over x. So what do we get is the equation x equals 1 plus 1 over x. Okay, so let me continue on this side. So we have x equals 1 plus 1 over x. Now let's multiply both sides by x. So you get x squared equals x plus 1. So x squared minus x minus 1 equals 0. You got a quadratic equation. Now we apply the quadratic formula. You get x equals 1 plus or minus the square root of b squared minus 4ac, which looks like 1 plus 4 over 2, which is going to give me 1 plus or minus the square root of 5 over 2. Okay, so that's what you get. That's what the sequence converges to. What's interesting is that this number, one of these numbers, 1 plus the square root of 5 over 2, is called the golden ratio. It's often denoted by phi. And what is the golden ratio? Well, this appears all over in the nature and also in design. So the Greeks, when they designed their temples, like the Parthenon, they designed the Parthenon as a rectangle, where the ratio between the length and the height of the Parthenon is given by the golden ratio. It's thought to be the most beautiful way to design a structure. And I think I'll stop here, and we will continue with section 11.2 next time.